Dispersion refers to the process of separating light into its various components. Cast your mind back, if you will, to Lesson 29 when we first discussed refraction of waves when they pass from one material to another. The wave bends because it changes speed if it hits the boundary at an angle. And for 95% of the problems you're going to solve in this course, the amount of bending doesn't depend on the color of the light that's involved. For our purposes, we've treated all colors of light the same. But if we're going to appreciate dispersion, then we have to recognize that some colors of light bend slightly differently than others. Why does this happen? Why do some colors get bent more than others when they cross a boundary? To begin to answer this question, you'll need to recall that different colors of light correspond to different frequencies. Violet frequencies are higher than red frequencies. I can say that because we know that the speed of light in vacuum, c, is equal to lambda times frequency, and the wavelengths for red light is about 700 nanometers is bigger than the wavelength for violet light at 400 nanometers. So that means that I've got to take the larger number and multiply it by a smaller frequency in order to end up with the same product of a smaller wavelength multiplied by a higher frequency. So when white light hits a material, the electrons of the atoms in the material are forced into vibration at whatever frequency the incident light causes it to shake. Violet light causes atomic electrons to shake at a faster rate than red light does. As a result, these atomic electrons tend to hold on to the higher frequencies slightly longer than they do to the lower frequencies. This means that the higher frequency light tends to lag the lower frequency light, and the higher frequency light travels more slowly than the lower frequency light does in the material. Translated into measurable quantities, that means that the index of refraction of the higher frequency light is slightly higher than the index of refraction of the lower frequency light. So if white light strikes a boundary at an angle, the violet light that's in this white light will be bent slightly more than the red light is, and the light is dispersed. As the light continues along its path, the farther along it travels, the larger the amount of separation between the colors. Basically, we say the material is more optically dense for the higher frequencies, and the index of refraction of the violet light is slightly larger than the index of refraction of the red light. So, how does this produce a rainbow? Rainbows are made when sunlight hits a whole bunch of droplets of water. This collection of suspended droplets of water serves as our refractor of the sunlight. The water represents a medium with a different optical density than the surrounding air. And there are gazillions of white light rays that interact with gazillions of water droplets. Of the countless paths by which the light rays from the sun can interact with the droplet, there is one particular path of great significance in the discussion of rainbows. So let's examine how a single white light ray behaves inside a single water droplet, and then we'll assemble a whole bunch of them together. Here's a diagram to guide our discussion. This diagram is numbered from 1 to 7, and we're going to write down the steps. In step number 1, light from the sun is incident at a slightly downward trajectory and hits a raindrop. Where it strikes, I could draw a normal to the boundary at that point. And number 2, some of the light is reflected from the surface of the drop, while at number 3, the rest of the light crosses into the drop. As the light enters the drop, the speed decreases, and the light bends toward the normal inside the droplet. The white light is composed of all the frequencies of the visible spectrum, and the higher frequencies shake the electrons in the water molecules faster than the lower frequencies too. So that means, number 4, that the different colors of light begin to diverge inside the droplet. The red light is bent less than the violet light is. Number 5, when the light reaches the rear of the droplet, it strikes with an angle of incidence that's greater than the critical angle for the water-air interface, and so the light gets totally internally reflected from the back of the droplet. Now we come to number 6. As the light reaches the other side of the droplet, it crosses the boundary from water back into air, and it refracts again. Finally, in step number 7, the light disperses even more as it travels away from the droplet. The original pencil of white light is now spread out, with different colors traveling in slightly different directions out of the droplet. Upon refracting twice and reflecting once, the light is dispersed and bent downward toward an observer on the Earth's surface. Since the boundaries of the water droplet are not parallel to each other, this double refraction results in a distinct separation of the sunlight into its component colors. The angle of deviation between the incoming rays from the sun and the refracted rays directed to the observer's eyes is approximately 42 degrees for the red light. Because the shorter wavelength violet light refracts more than the red, its angle of deviation from the original sun's rays is approximately 40 degrees. The red light refracts out of the droplet at a steeper angle than the violet toward an observer that's on the ground. While there are a multitude of paths by which the original ray can pass through a droplet and subsequently angle toward the ground, the greatest concentration of outgoing rays is found at these 40 to 42 degree angles of deviation. At these angles, the dispersed light is bright enough to result in a rainbow display in the sky. So much for an individual droplet. How do many droplets form the rainbow? A rainbow is most often viewed as a circular arc in the sky. An observer on the ground sees a half circle of color with red on the outside or the top of the rainbow. Standing on the ground, you can only see the top half of the circle, since the bottom half is prevented by the presence of the ground, because suspended droplets can't be present below the ground. If you're fortunate enough to have seen a rainbow from an airplane in the sky, you can actually see a complete circle, like in the picture that was there at the beginning of this lesson. The arc results because there are a collection of suspended droplets in the atmosphere that are capable of concentrating the dispersed light at angles of deviation of 40 to 42 degrees relative to the original path of the sunlight. These droplets actually form a circular arc, with each droplet within the arc dispersing light and reflecting it back towards the observer. Every single droplet within the arc is refracting and dispersing all of the visible spectrum, Roy G. Biv, but the red light is refracted out of each droplet at a steeper angle toward the ground than the violet light is. Then, when you sight at a steeper angle with respect to the ground, droplets of water within this line of sight are refracting the red light toward your eyes, while the blue light is refracted by the same droplet passes over your head. In a similar way, when looking at a less steep angle, the droplets of water within this line of sight direct blue light to your eyes, or violet light, and the red light from the same droplet is directed downwards at a more steep angle toward your feet. So, the red light appears on the top or outer side of the rainbow, while the violet appears at the bottom or the inside part of the rainbow. Rainbows aren't limited to dispersion of light by raindrops. Any kind of misting water in the air can result in the formation of these beautiful structures. Splashing water at a waterfall, or a backyard water sprinkler are other common sources of rainbows. But there are three necessary conditions for rainbows to be observed. One is that you have to have bright sunlight at your back. Two, you've got to have suspended droplets of water in the air. And three, you have to have the proper sighting angle. And if those three things come together, then you have the opportunity to view one of nature's most splendid masterpieces. To review this lesson, we've talked about total internal reflection. What is necessary in order for light to be reflected at a boundary instead of refracted across the boundary. We've discussed dispersion, and we've talked about the production of a rainbow. That's enough for right now, and for this lesson, that's it.